Okay, set. So, it's 15 Spanish. Okay, hoy tenemos el mucho gusto de recibir al doctor Stephen Carey, que trabaja en la Universidad de Rhode Island, Estados Unidos. Y Stephen Carey es realmente uno de los padres de la volcanología moderna y son los trabajos fundamentales para cuantificar realmente las erupciones más explosivas. Y yo creo que muchos de sus trabajos, bueno, los recomendamos, los damos a leer a nuestros estudiantes de clases básicas de volcanología. Yo creo que es uno de sus logros más importantes. Y bueno, aparte de eso, bueno, ha trabajado sobre el Monte Santa Elena, sobre el Chichón, vino aquí después de la erupción de 1982, hizo un trabajo también muy importante sobre los depósitos de oleadas piroclásticas, trabajo sobre las erupciones gigantescas del Tambora, y desde unos años, porque ya veía que en los continentes básicamente sabemos más o menos cómo las cosas funcionan, pero ahí abajo del mar, bueno, realmente hay muy poco que se sabe sobre el volcanismo abajo, y es lo que me estuvo platicando de hecho ayer a la noche, y creo que si realmente imaginamos que todos son puras lavas, y realmente hay volcanismo explosivo ahí también, ¿no? Y entonces ha dedicado más a estudiar ese tipo de volcanismo en los últimos años. Ha participado en muchos cruceros, barcos para estudiar todos esos fenómenos. Y yo creo que nos va a contar más sobre todo eso ahora mismo. Muchas gracias.
Thank you very much. It sounded like an impressive introduction. I'm sorry, I didn't understand it. Can you all hear me okay? Yeah, okay. So thank you for inviting me. It's very nice to be back here at the Instituto de Geofísica. Last time I was here was over 30 years ago, and I was collaborating with, where is he? Juan Manuel Espindola, right here, my good friend, when we worked on El Chichon volcano in 1982. So been away for a long time, but it's very nice to be back. Today I'm going to be talking about submarine volcanism. So I spent most of my career studying volcanoes on land. Now I've moved into the ocean. And let's see, whoops, sorry. There's a lot of things to control here. When people learn that I'm a volcanologist and I tell them that I'm at the Oceanography department at the University of Rhode Island, they look at me and they say, why is a volcanologist at an oceanography department? And so the answer to that, and one of the major things that I always try to tell my students, is that 75% of the Earth's volcanism actually occurs in the ocean out of sight. And so to be a volcanologist and be at an oceanography department actually makes a lot of sense. So most of the Earth's volcanism occurs at mid-altitude spreading centers, as you are probably all aware. And this volcanism produces a very common type of volcanic lava, which is called pillow lava. Pillow lava is the most abundant type of extrusive volcanic rock on planet Earth. So the entire ocean basins are floored by pillow basalts. And so most of the Earth's volcanism is extrusive or effusive, okay? But about 10% of the Earth's volcanism occurs at oceanic islands, and some of this volcanism is explosive. So I put an example up here. This is the island of El Hierro in the Canaries, which is a hotspot. And in 2012, there was an explosive eruption at relatively shallow depth. And so we do have oceanic volcanism that is explosive, but it's very limited in scope. The factors that determine whether we have explosive versus effusive volcanism in the ocean depends on a lot of different parameters. So up here, I have different types of processes that produce or will fragment magma into pieces. So it ranges from what we call magmatic explosivity. This is when dissolved gas in the magma expands, and that breaks the magma up into pieces. this rather cumbersome term here, steam explosivity. This is when magma mixes with water and that flashes to vapor. It's phreatomagmatic activity. That's a way in which you can fragment magma as well. And then finally, we have something called cooling, contraction, granulation. This is thermal shock when magma interacts with water and it essentially breaks magma up into small pieces. So this diagram attempts to show you as a function of water depth how these different processes interact with magma. The depth range for most mid-ocean ridges, where most of the Earth's volcanic activity occurs, is very deep. And so the processes of fragmentation are rather limited. In shallow water, this is where we typically find explosive volcanism. And this explosive volcanism in general is driven by magmatic explosivity or the exsolution of gases from the magma. So there is a strong dependence on depth of the behavior, of the nature of the type of submarine eruption that will occur. And again, most basaltic volcanism in the world's ocean, occurs at very deep levels and is effusive. So we're going to be looking at, today I'm going to be talking about this window, a relatively shallow depth, where we have a whole multitude of different kinds of processes that can fragment magma. Klaus is going to be very angry at me because I'm going to be talking about a style of eruption which is called basaltic balloon eruptions. And this is the last time you will see the word balloon in my presentation. From further on, we will call them buoyant scoria. But this term, unfortunately, is entrenched in the literature. And what this refers to is an unusual style of shallow water volcanism that produces very large meter-scaled scoria that rise all the way to the surface. They give off gas and they sometimes explode. So they are a hazard. They're a kind of geologic hazard. But they eventually fill with water. So this is an example of one eruption. These will eventually sink back to the ocean floor. So the phenomena, the observed phenomena is fairly transitory. The term balloon essentially is derived from some observations of some of these clasts that look like this, where the inside of the scoria is one large gas cavity. And then on the exterior, we have this quenched rim. So this term has gotten into the literature. Unfortunately, many scoria do not look like this. They do not have this typical shape. So going forward, we're going to be talking about buoyant scoria. So this style of volcanism is rarely observed. There are only 5 historic examples of this style of shallow water explosive volcanism. One in Pantelleria in the Mediterranean, one in the Canary Islands, one in the Azores, one in Socorro, Mexico, and one in Hawaii. So during the whole historic period, these are the only events that we know of that have this style of activity. Today, I'm going to be talking about 2 of these, which I've been working on during the last several years by looking at the vent areas from these eruptions. So the first one I'm going to talk about is the 1891 eruption off the island of Pantelleria in the Mediterranean Sea. The second eruption that I'll be talking about is a 1993 eruption off the island of Socorro, Mexico. So the objective, what we like to do is to try to determine the processes and conditions that form these large buoyant scoria, not balloon, but buoyant scoria, by exploring the vents. So the problem with this style of volcanism is what you see at the surface, the sea surface, really doesn't tell you much about what's going on at the vent. So if you really want to understand the processes of the formation and the evolution of these kinds of eruptions, you need to go down where the source of the eruption is. And so that's what we've essentially done. I'm going to talk a little bit about the technology that we use. I apologize. So this is going to be an overlap. If people came to my talk yesterday, I'll go through it a little quickly. But the technology is important because it really determines how we go about exploring these vent areas. So during the last decade, I've been closely collaborating with Dr. Robert Ballard, who is a faculty member at the University of Rhode Island. Many of you may know he's a very famous oceanographer. He discovered the Titanic. He discovered the black smokers on the Pacific Rise. So he's very well known in the oceanographic community. He is at Rhode Island. And Dr. Ballard operates his own ship, which is the Nautilus. And this is a ship, so-called ship of exploration. It's operated by the Ocean Exploration Trust. And Dr. Ballard has pioneered this concept or method of exploring the ocean floor, which he refers to as telepresence. And the concept of telepresence is as follows. So you have a ship out at sea. In this case, you have the Nautilus. And the Nautilus is exploring the ocean floor using a robotic vehicle. That vehicle has video cameras on it. It has sensors on it. It's transmitting all of that data up a fiber optic cable back up to the ship. And then what happens is there's a satellite dish on the ship. All that information is relayed in live feed by a satellite back to this inner space center that we have at the University of Rhode Island. This is a mission control center which controls the data which is flowing from the real-time observations on the ocean floor. So the ship can be anywhere. It can be anywhere in the world. And the video feed, what you see down here on the ocean floor, you essentially is distributed by mission control to a website. This website is called Nautilus Live. And if you go on your mobile phone or if you go on your laptop computer or in your office, you can watch in real time exactly what the ROV is exploring on the ocean floor. So this was Dr. Ballard's concept to open up the excitement of discovery, of exploration of the ocean to the world. So in the old days, during a typical oceanographic research cruise, you would have about a dozen scientists on board the cruise. And those would be the only people that would be seeing what's going on down here on the ocean floor. But now, through telepresence, essentially what happens is you engage the entire world in the excitement of discovery. The other thing that telepresence does is it allows you to have more scientists involved in the research. So you could have an expert on fishes who is in California, in Mexico, or wherever, and is watching live on the computer. And if you see something interesting, if you see a new type of fish, say, oh, that's an important discovery, take a sample. So it allows for this really wide distribution live of what's going on the ocean floor. So that's a little bit about telepresence. I'll say very quickly about the technology, the vehicles that we use to explore the submarine volcanoes. The first is a very large, sort of industry class, remotely operated vehicle called Hercules. Hercules has high definition video cameras on it. It's got a manipulator arm for taking samples, and it's got a whole suite of onboard sensors, CTD mapping capability. Hercules twin is Argus. This is another ROV, which also has high definition cameras and a suite of onboard samples, sensors. It does not have manipulator arms, so it can't grab samples. But these two vehicles go down together. And so Argus rides above Hercules. So I'll turn this mic off. So we've got Argus and Hercules down here, and they go down together. And what that allows for is Hercules to be able to roam around without being tugged by the ship. So Hercules is connected to Argus by this tether. And it allows a very stable, I'll go back here. It allows for a very stable operation of the vehicle. So this is the tether that goes back up to Argus. It supplies all the power. All the video and data go back up in the other direction, up to the ship. So this is a phenomenal tool for exploring submarine volcanoes and for taking samples. So in the old days when I used to go to a volcano, I'd have a backpack on and a rock hammer. And now I use this fancy tool. Okay, on to the eruptions. So the first eruption I'm going to talk about that we studied with Hercules and Argus is the 1891 eruption of Forstner volcano in Pantelleria. So here's a map to locate ourselves. This is the island of Sicily. This is North African coast. The island of Pantelleria lies here in the Pantelleria Graben. So it is a small extensional basin. Some of you may be familiar with Pantelleria, the famous rocks of Pantellerite derived from here. They're peralkaline rocks, very unusual in composition. So there was an eruption of submarine eruption off the coast of Pantelleria, which is shown in this old lithograph, which I found, where you had large buoyant scoria, which came to the surface and were venting steam. So a little bit about the eruption. This is the island of Pantelleria. The activity began on October 17th, 1891. And it continued for about 1 week. So it's a very short eruption. And I'll talk about Socorro later. Socorro was a much longer eruption. Pantelleria was over very quickly. Interesting thing about the Forstner eruption was, even though it occurred offshore of Pantelleria, there was increased seismic activity and increased fumarole activity up here at the summit caldera. So there was some connection between the magma ascent that led to the eruption out here and the main volcano here. So it occurred about 4 kilometers off the west coast at a water depth of 250 meters. So this water depth, about 200 to 300 meters, you're going to see is a very common feature of this style of volcanic eruption. And I found it interesting that, so this old lithograph, the locals on the island of Pantelleria, when they first saw this eruption, what they thought was this was a group of whales who had come to the surface and were spouting. And so the local fishermen went out with their boats to investigate to see what was going on. And they found these giant hissing scoria blocks, some of which, when they broke them open, they were still incandescent, red hot inside. So they were obviously not whales, and they didn't know what to do with them. This is a bathymetric map, a detailed bathymetric map. Here's the coast of Pantelleria. So this is what the offshore geology looks like off of the island, and it's very interesting. You can see it's made up of a whole series of very small cones, kind of satellite cones. And for those of you with a keen eye, you can see that some of these cones have beautiful horseshoe-shaped scars that looks like there was collapse feature. There's one right here. The site of the 1891 eruption was right here. So this little, you see this little tiny nub right there? That's where the eruption occurred. So it didn't produce a very large physiological feature. It was in fact a very, very small event. Well, we went there with the Nautilus and we explored this area with the Hercules ROV. One of the things that the Hercules ROV can do is it has a multi-beam sonar on the vehicle, and so it can do very high resolution bathymetric mapping. You can get bathymetric mapping with resolution of 2 centimeters, which is, as you know, is absolutely remarkable. And so what you see, these are actually individual rocks that we've been able to map with the sonar. The general configuration of the vent is not so interesting if you're interested in geomorphology. It is basically 2 small cones that just come to a peak. There's no real crater. It is literally just a large pile of rubble. So I'll show you a video here of what it looks like to explore. It's like, oops. Turn the sound up. Oh, sorry, you can hear the sound. So we're going along with the ROV, basically what you can see is these are giant scoria blocks, and you can see they have large gas cavities in them. So over here, as soon as you move around, there's lots of small scoria. This is another large scoria here. Here's one with a very large gas pocket in it. Here's one that's sort of oblate shaped. And there's a lot of small scoria here that are about the size of your fist. One thing I want you to notice about this is there's very little fine-grained material at this vent site. So it's very kind of coarse and rubbly. When we come down here, you get a kind of close-up view of what one of these looks like. So these are similar to what will have gone up to the sea surface, but then eventually fill with water and then sank back down. So we collected some of these samples. This is the largest volcanic rock sample that's ever been collected by the Hercules ROV. It is about more than 1 meter in diameter. And the way we collected it was we took the manipulator arm, we hugged it, and we pulled it on to the front of the vehicle. And then as the vehicle went up, we just held onto it with the arm because we didn't have a sample bin that was big enough to put this rock in. The only reason we could sample this rock is because it looks like this. If this was a solid rock, there was no way you could lift this up with the Hercules ROV. It'd be too heavy. But when we got this rock up on deck, it broke open, and this is what it looked like. So the inside is virtually hollow, and there's this crust that sort of forms around the outside. So the density of this class is very, very low. So the actual weight of it is not very much. So we were able to lift it up with the Hercules ROV. The ROV continuously records video of the ocean floor, and so we can use that video systematically to come up with basically a geologic map of what the vent site looks like and to identify different facies or different types of volcanic deposits that make up the vent area. And so this is really the basic information that we need to make an interpretation about how the eruption actually occurred. So I'll look at I know this is probably difficult to read, but there's a couple ones I want to emphasize. The first is spatter. So this is this area right up here. There was a facies near the top of this, which looked like spatter. If any of you are familiar with spatter at Hawaiian volcanic eruptions, this is clasts that are very plastic and hot that fall on top of one another and sort of weld together. So we found a little bit of it here and a little bit over here. Most of the cone is made of what we call scoria bomb beds, pillow lavas, and bombs and pillow lava flows. In general, what I want you to get out of this is that most of this cone, and I'll show you some pictures of this in a minute, is all clastic. There's a very small proportion of pillow lavas or extrusive material here. So this is what we were calling, or what we interpret as a spatter or agglutinated deposit. So this is sort of plastically deformed clasts that are sort of welded together and form these kind of bulges or spurs. But this is not particularly abundant at this particular location. Most of the side of the vent here consists of these isolated large blocks of scoria, some that are broken open, some that have very large gas vesicles in them, a little bit of sediment in between. And then there's some pillow lavas. So again, these are not particularly common, but they do occur. But the majority of the vent site is this very coarse volcanoclastic material. So what's happened at the vent? How do these large scoria blocks form that rise up to the surface? So based on our observations, this is the first go that we had at thinking about what was actually going on at the vent site. And initially we called this kind of a hybrid Strombolian style eruption. So we envisioned something like rising magma that was very rich in gas, and that magma fragments principally due to volatile exsolution. It's extremely gas rich. The magma fragments, most of it accumulates around the vent, but there are pockets of very rich, gas-rich magma, some of which actually make it up to the surface. But an important point, I think, and one thing that now Klaus and I are thinking very carefully about is that actually these scoria that you see on the ocean surface is a very, very small subset of the products that are occurring down here at the vent. Most of the stuff doesn't make it to the surface. These are like unique or special pieces of magma that have excess gas in them and what allows them to buoyantly rise. So I call this Strombolian, but in fact, truly Strombolian activity is difficult to envision on the ocean floor because most Strombolian activity on land involves a free magma surface where large bubbles rise and then burst. That's likely not to occur in the ocean because the magma is quenched very, very quickly. So later on in the talk, I'll go into a modification of this model. I should say, if anyone has any questions while I know I have to give this in English and I apologize for that, but if you have questions, please feel free to raise your hand and ask. Okay, the second eruption I'm going to deal with is the eruption of Socorro, Mexico, so close at home for most of you. Socorro Island is part of the Revillagigedo archipelago. It consists of a number of islands out here, San Benedito, Roca Petita, and Clarion. And there was an eruption in 1993 that Klaus Siebe here was a witness to. The eruption began on January 29, 1993, and it continued at least until April 1993. So this event was much longer lived than the one at Pantelleria. It was first detected by SOFAR hydrophones, so these hydrophones that they have in the ocean that are nominally used to track submarines and other activity, they picked up acoustic signals of the eruption about 10 days before. And so this is a map that I extracted from Klaus's paper. Klaus wrote the seminal paper about this eruption. And so the area where the floating scoria were observed is located about here. This is the coast of the island of Socorro. And it wasn't known precisely, but the depth of the vent was anywhere from 30 maybe to 210 meters down. One of the interesting features of the Socorro eruption is that inside some of these large scoria blocks, Klaus found this material called reticulite. Reticulite is actually, I think it's one of the most beautiful geologic materials I've ever seen. Klaus has a sample at his house, and it is, I characterize it as ultra vesiculated. So it is the highest vesiculated magma that's been recorded. So it is virtually all bubbles. And so Klaus put a piece of that on my hand yesterday, and you can't even feel it on your hand. It is so light. So the formation of this obviously requires very special circumstances. You can't form this, we think, in contact with water. This is found inside most of the scoria blocks themselves. So Klaus also passed on to me yesterday some photographs of the eruption. And you can see this looks very much like the lithograph of the Pantelleria eruption, where we have these large scoria blocks that floated to the surface. Some of them are exploding. Many of them are giving off gas. It's probably steam. So water percolates inside the scoria, it gets heated up, it's flashed to steam, and it comes out. Some of these are actually propelled across the water by this stream, this jet stream. So they're very nice images. And we also have a video of the eruption, which turns out to be extremely instructive. So last year, almost exactly 1 year ago to the day, we ran a Nautilus cruise to Socorro Island to try to go back. Klaus was with us to try to go back and find the vent. So no one, since 1993, no one had ever found or explored the vent to this eruption. So we went back with the Nautilus and with the Hercules ROV. The first thing we did was to multi-beam the area. So we produced a very high precision, high resolution bathymetric map. And this is the area where the observations of the floating scoria occurred. And so this is the area that we focused on to explore to try to find events. So you can see, just like off of Pantelleria, the sides of the island of Socorro are sort of littered with small volcanic cones and constructs. And the area where we looked for the vent is kind of a complicated series of ridges and small cones. So to zoom in, the first dive that we did, so this is a zoom in of this area. This is this series of ridges. We started the dive with the ROV up here, and we explored each of these peaks, trying to find the source. Where did this eruption come from? And it was long into the dive, and we saw some interesting geology. We saw some fairly fresh volcanic rocks, but we weren't convinced that we actually found the vent. And then we traversed over to this ridge here, and this is where we think the vent actually occurred. And I'll show you a video of what that looks like. So this is the view out of the front of Hercules, and we're moving upslope. You can see two little dots here. These are laser dots. These are scalars. These are 10 centimeters apart. So they're used for scale, so you can look at the features. So as we came up the side of this small ridge, we started to notice all this yellow bacteria. Lots of abundant scoria, lots of very fine-grained material. And then when we got very near the top, we started to see these patches of white. This is also bacteria, and this is the sort of summit of that area. Very large broken scoria pieces here sitting on the seafloor that are sort of surrounded and embedded by this white bacteria. Again, here's a scale. This is 10 meters inside. This is a very large scoria here, so this is like several meters in size. This is an oblate one shaped here. It's about a meter or so. But the bacteria really sort of gave it away. If this was the site of a recent eruption, you'd expect some remnant heat from the eruption that could drive the generation of a hydrothermal system. And in the Canary Islands in the 2012, when they went down to look at the vent there, they found an active hydrothermal system. So we thought, okay, this must be the site, because this looks like the freshest volcanic rocks, and we have hydrothermal activity going on. A very interesting sort of side discovery of this was this white bacteria. So this bacteria, and I'll show you a video in a second, it's very fine-grained, very filamentous. It looks like hair, and it's found all in the crevices of the scoria. So the scoria, all this bacteria is sort of living in here. We did do a temperature probe here, and there was an anomaly of only about 1 degree or so. But in the spring, after this cruise, I came across a paper by Danabaro et al. That was published in 2017 by a group who had looked at the vent from the 2012 Canary Island eruption. And this is what they found at the top of that vent. They found this white filamentous bacteria surrounding the basaltic scoria. They did genetic analysis on it, and they discovered that it was actually a new species of bacteria, which they named Theolaba veneris, or Venus's hair. The interesting thing about this bacteria is it has multiple metabolic pathways. It means it can live both from fluids that are coming out of hydrothermal systems, but it can also survive in sort of background oceanographic conditions. So this is a kind of bacteria which is ideal as a colonizer. So we have a volcanic eruption, and we have fluids that are coming out. This is a kind of bacteria that can quickly colonize an area. And I think it's fascinating that we see virtually the same bacteria in the Atlantic, so that's where the Azores are, and the Pacific. So the question is this bacteria kind of throughout the ocean and ready to colonize where we have new volcanic eruptions? So that's the extent of the biological part of this lecture. I'll show you a video of what this looks like. It's very neat stuff. We're going to zoom in and focus, and so this is what it looks like. It basically looks like hair. Very fine grain, bilifilamentous, and is in all the cavities of the scoria. But the bacteria, I think, is useful because it marks the place that probably has the highest heat remnant from the eruption. So it's like a marker of where the vent was. Okay, so what kind of volcanic products did we find at the Socorro vent? So there are basically two kinds of, I think, of important volcanic products that we see at Socorro. The first, very, very abundant basaltic scoria with very large gas cavities of varying sizes, all the way from fist size to a couple of meters in diameter. The other volcanic product that we see at Socorro, which we don't see at Pantelleria, is very abundant volcanic sand. So you see lots of, this is actually a pillow lobe, but you see that within and between a lot of these scorias is this black, dark volcanic sand. And if you look at this under a microscope, under the SEM, this is what you see. So this is classic volcanic ash, shard particles, basaltic, completely glassy, bordered by bubble walls. This is sort of classic kind of tephra that's produced by explosive eruptions where the gas is fragmenting the magma. So what is the origin of the scoria and the volcanic sand? So we have to explain two things. There are two important volcanic products there. There's these big scoria that go all the way up to the surface of the ocean, and we have this volcanic sand. So how are they related? What are the volcanic processes that produce each of them? I'll show you a couple slides of the different, what the sort of common volcanic fascias look like. Some of these are quite colorful and beautiful. So this is a very typical view at the vent site where we have abundant basaltic scoria with yellow bacteria and white bacteria intergrown. This is an area where we have large quantities of volcanic sand, some of which was redistributed by currents, and you have ripples on it. Also colonized by bacteria, and you have a few scattered scoria like here. And then the other volcanic type of extrusion is pillow lavas. And these are the most unusual pillow lavas I've ever seen in my career. So I've done a lot of diving on pillow lavas before. Pillow lavas are usually formed by effusive activity, and they are very dense, very hard. These pillow lavas were extremely vesicular, almost like consisting of scoria. And when we went to try to sample these pillow lavas, usually if you try to sample a pillow lava with an ROV, you can't do it because it's dense lava. These pillow lavas, when we went up with the manipulator arm and tried to grab it, it just crumbled in the manipulator arm. And then we saw lots of interesting features where it looks like you had the remnant of a pillow lava tube, and then the end of the pillow has been expanded and blown out. This looks like a piece of broccoli or a piece of cauliflower. Some of these pillow lava features, this is one of my favorite photographs, this is a pillow lava tube that runs all the way across the image. You can see it here. And in the middle, part of it's missing. But on the sides of it, you have pieces that look like, maybe I could fit that back into the pillow lava tube. So the question is some of this very vesicular pillow lava actually being disrupted and potentially form scoria? And finally, these are very interesting features that we found. These are kind of hornito-like features, which consist of very chaotic lava, extruded, very vesicular, in very chaotic kinds of positions. Here's one that looks like a hollow shell, surrounded by a lot of volcanic sand, though. But some of them look like they're shooting straight up, heading for the sea surface. And I'll show you a video. So here we see lots of giant scoria embedded with lots of volcanic sand. This is a kind of oddly shaped one. Now we're getting onto this hornado-like structure, which you can see is filled with these cavities, but the structure is extremely chaotic. Not like a normal pillow lava extrusion, but something that looks like there was perhaps buoyancy involved in its emplacement. And we're going to go around to this area right here. This is a broken piece that looks like it's been broken off, but inside you can see evidence that there were multiple injections of magma. So we have this external part here that looked like there was a large cavity, perhaps a gas cavity, and then there was another extrusion of magma that formed this little almost micro pillow inside. I've never seen anything like this before. Looked at a lot of pillow lava examples, but you see this is all very scoriaceous. So the origin of this is potentially interesting. So I want to talk about now, we had one model of how these buoyant scoria might form, and that is like a modified Strombolian activity. This is a diagram from a paper that was produced looking at the Canary Island eruption in 2012, which is the most recent giant scoria eruption. And the is as follows. So they suggest that there was a vent which was explosive, very gas-rich magma, which is rising toward the surface. And then there was a gas-driven jet, which produced a very energetic eruption column that actually bowed the surface of the ocean, contained very high quantities of fine volcanic ash, and acoustically, they actually saw the eruption column collapse and form gravity flows consisting of fragmented material that went down slope. And out of this eruption sequence, these buoyant scoria were also formed. And so they essentially thought that the origin of these buoyant scorias were related to this very energetic discharge by a gas-driven jet, which was characterized by very high degrees of fragmentation. I'm calling this, on the spectrum of mechanisms to produce these giant scoria, I'm calling this the explosive end member. Another model that was proposed for the eruption in the Azores by Forzat in 1991 thought differently about the way these buoyant scorias were formed, and they thought that this particular eruption was strongly graded according to water depth. So they thought that at water depths of about 200 meters, you had almost complete fragmentation of the magma, generation of volcanic ash that just went up into the water column. But at deeper levels, at about 400 meters, with increasing pressure, you had pillow lavas that were very gas rich and which detached as pods and then rose to the surface. So on the spectrum of mechanisms to form these buoyant scoria, I'll call this the effusive end member. So we have models that suggest that the buoyant scoria are formed by very energetic explosive eruptions, and we have models that are produced by effusive activity. So what's the answer? Well, the observations that we made at Socorro, and actually my feelings about this have changed over the last day with discussions with Klaus. I think we see evidence of both processes. I don't think you can assign a single eruptive process to these types of eruptions. So some of the evidence that I'd like to point out. So some of the scoria lie in close association with vesicular pillow lava outcrops. So that pillow lava tube that I showed you and sections of it were missing and on the side suggests, well, maybe parts of these pillow lava tubes broke off and rose to the surface. So effusive. Some of the scoria, not all of them, have extrusion ridges that are similar to those produced by pillow lava extrusion. So this suggests maybe they were produced by an effusive mechanism. Yesterday, at Klaus's house, we looked at the video of this eruption. And this observation, I think, is absolutely critical to the interpretation of the eruption process. Is that in the video, what you see is large quantities of these buoyant scoria came to the surface simultaneously as a single pulse. And so you have a big area of floating scoria, and then they essentially sink back down, and then you get another pulse. This mechanism then is really not coincident with having them formed by lava flow. It's very difficult to envision how a lava flow could generate a whole series of these things in one single pulse. So this, I think, points to a more explosive part. And then finally, when we look at the images of the scoria on the sea surface, their shapes are extremely irregular. So they don't look like pillow lava pods that have risen off of pillow lava. They look like something big that's been disrupted. So you can see we've got evidence for one type of mechanism and evidence for a second type of mechanism. So I'll get back to the scoria in a second. The other thing that we have to explain is what's the origin of all this volcanic sand. So the cone itself is built up of extremely large quantities of this material. This is an SEM photograph of these very highly vesicular shards. And again, these are very characteristic of the kinds of shards that you form when you have fragmentation by exsolution of gases in the magma. So if you see these on land or you see these in the water, the shapes and the morphologies of things suggest that they are formed by degassing. So this is an explosive process. So now we have parts of the products on this scoria cone are clearly pointing towards explosive. So how do we pull this all together? Well, this is this old slide that I showed you where this model had at shallow water, it had highly explosive activity. At deep water, we had effusive activity. We think, or in my opinion now, is that we can have both explosive fragmentation and diffusive going on at the same depth. They don't have to be separated according to depth. You can do this at the same vent simultaneously. And I think there is evidence for that. There are very few submarine explosive eruptions that have actually been observed. One of the ones that was observed is in the volcano called West Mata. It was recorded in 2009 by an ROV. This is in the Western Pacific. This is one of the few video documentations of what a submarine explosive eruption looks like. And so what I want to show you is that dramatically what this video shows is at the same vent, you have explosions going on and you have lava flows going on simultaneously. So I'll play this. There's an explosion which produces highly fragmental material. Here's a lava flow which is flowing down slope at the exact same time. So we have explosions that are highly fragmented. These are producing scoria. And at the same time, we have a lava flow which is moving down slope and forming pillows. And so clearly, this is an example where there's not one kind of mechanism that's going on. There are two mechanisms occurring simultaneously. Is that me? Sorry about that. Sorry. So, as I say, there are very few examples of submarine explosive eruptions, but I think this is very interesting in the context of Socorro, that you can indeed have explosive and effusive activity occurring simultaneously. Okay. So the model that we think that we're toying with now is that at Socorro, we had effusive activity of very gas-rich magma that may have formed like a carapace or a plug that was then episodically disrupted, broken up, and parts of that carapace were gas-rich and came all the way up to the surface, whereas other parts of it stayed at the vent. But at the same time, where you had this blockage of the vent, there must have been almost continuous explosive activity generating this volcanic sand, which you can see from that video can occur. You can have explosions going on, and you can have effusive activity going on simultaneously. So the fact that we think the system is dominated by explosive activity driven by gases, the question is, do these unusual kinds of buoyant scoria eruptions, are they characterized by magmas that have unusually high gas contents? So this is another aspect of the study that we've been working on. This is a thin section. This is a backscattered electron image of a thin section of the scoria. So these are gas bubbles. This is the glass. And these contain crystals, which crystallize in the magma. And these crystals contain melt occlusions. And many of you may know that if you want to determine the gas contents of magmas before the eruption, you can analyze these little cylinders, these little aliquots of melt, because these have not been degassed. So these little melt inclusions trap the original carbon dioxide and water content of the magma when it was at depth. And so we have them in a number of different crystals. You analyze those with an FTIR, so Fourier transform infrared spectroscopy, and this allows you to examine the degassing behavior of the magma. So, do they have very high gas contents? These are the results. This is carbon dioxide on this axis. This is water in this axis. So this is all melt occlusion. So these are all data from the melt occlusions in crystals. This is a field of mid-ocean ridge basalts, a global compilation of melt occlusion data. Mid-ocean basalts have very low contents of water and very low contents of carbon dioxide. This is the field for the Hawaiian Islands. So you can see the Hawaiian hotspot has higher contents of water and higher contents of CO2. This is Socorro. Red dots are all Socorro analyses. These are analyses from Pantelleria. And these are analyses from another buoyant scoria eruption in the Azores. So you can immediately see that compared to mid-ocean ridge basalts, compared to Hawaiian Island hotspots, that these magmas are indeed greatly enriched in carbon dioxide and water. So we're looking at 3 of the 5 historically documented giant scoria eruptions, and they all seem to have high gas contents. In fact, Socorro has the second highest carbon dioxide content of any oceanic basalt measured in the world. There's only one basalt that has higher CO2 content, and that's a scoria sample from the Juan de Fuca Ridge, and that has 9,000 ppm. Yeah. There are no analysis for Hierro. Not that I know, nothing's been published yet. So this is the only data that we know so far. So yeah, for 3 out of 5 of them. So I mentioned that, so one of the things that you can do with melt occlusion analysis of carbon dioxide and water is you can evaluate the degassing path that the magma took as it went from depth to the surface. And you can calculate paths of degassing. So all this data, all the red data, this is all Socorro, but these are from different crystals. So these are from olivine, these are from plagioclase, and this is the glass, the degassed glass. So this has virtually no remnant material. So those of you who are familiar with kind of degassing paths, there are two ways in which magma can degas. One is called open system degassing, and that is when the magma is rising to the surface, gases come out of solution, and they're lost to the system. And on a CO2 H2O plot, these are isobars. This is 3,000 bars, 2,000, 1,000 bar. An open system degassing path, if it's perfectly open, would predict a path that looks like this. So because carbon dioxide has a low solubility, it comes out of solution first before water starts to exsolve. The other kind of degassing that could occur is closed system degassing. So as the magma rises up, the gases come out of solution, but the bubbles stay with the magma as they rise. Closed system degassing produces paths that look like this. So there is an equilibrium between the carbon dioxide and the H2O content. And so, I mean, sometimes it's difficult to interpret these degassing paths because they're scattered in the data, but the closed system seems to better fit the Socorro data. The problem is that these curves are all generated by a computer program called VolcaCalc, and these predict that you have very high contents of starting CO2, really unrealistically high contents of CO2. So the way in which you can actually get the data to shift over in this direction is that if you influx CO2 to the magma from other magma that's been degassing. So this has been proposed for a lot of volcanoes, and there's like Strombolian eruptions typically have excess CO2 which is fluxing into the system. And the sort of fingerprint of that is when you shift these data points towards lower water contents, but retain high values of carbon dioxide. This has been suggested for volcanoes like Etna. And because Socorro has such a high CO2, it's not unrealistic to think that there was excess CO2 bubbling through the system. With this volatile data, you can take it one step further and you can start to do some modeling about how would the eruption proceed if you had this kind of volatile contents. So we used a degassing program called Decompress, and essentially this allows you to specify a certain CO2 and water content and starting pressure. The program you then specify the ending conditions. So we started at the highest CO2 level at Socorro with 1% water and 4 kilobars saturation pressure. The ending conditions are where the vent was, 250 meters water depth. So if you run that program, what it yields is that under closed system degassing, what you would generate is a scoria that has 85% volume of bubbles. And so the question was, do these magmas have enough gas in them to produce buoyant scoria? And the answer is yes, because you only need 60% volume of bubbles to make the scoria buoyant in seawater. Okay, so some conclusions. I think what the studies have shown is that explorations of the submarine vents by ROV or whatever process are very important to understand the processes of these scoria eruptions, because you really can't understand what's going on by just looking at the surface phenomena. I think what we're seeing is kind of what we're coming to a consensus is that these large buoyant scoria may be formed by a combination of both explosive and diffusive activity. So we can't assign one end member to the spectrum. We think that there are both kinds of activity going on simultaneously at the vent area. And finally, we'll see if this applies to some of the other eruptions, is that, yeah, in fact, these scoria eruptions do seem to be characterized by magmas with very high gas contents. And so I'd end by saying that these eruptions are really unique in that they illustrate that you need a very special combination of magma composition, volatile content, and water depth, probably to generate this style of activity. It doesn't occur over a large range of depths. It doesn't occur over a large range of magma compositions, and it doesn't occur over a large range of volatile contents. So it's a very special sequence. And all of the documented buoyant scoria eruptions have vents that are in this depth range, 200 to 350 meters. So if you found this kind of volcanic facies, these kinds of volcanic products in an old uplifted sequence, then what it really tells you is it's telling you something about the paleoenvironmental conditions where the eruption took place. So this is a very valuable kind of paleo depth indicator for interpreting ancient volcanic sequences. So I'll end there with a thank you, and I'd be willing to take some questions.
Bueno, muchas gracias por la plática. ¿Alguna pregunta, Hugo?
Thank you for very interesting talk. I was wondering if the gas content proportion has to be with the geodynamic setting. As far as I know, the rocks of Socorro Island have trace elements and rare earth elements that indicate that the rocks are related to plume, mantle plume related more. I don't know, I'm not familiar with the other sites, but they seem to be N-type more. So will it be a possibility that this setting has to be with a normal or in a larger amount of gases in this type of environment?
Yeah, it's an excellent question, and I didn't point out the fact that, in fact, all of the historic buoyant scoria eruptions are associated with hotspots or inferred hotspots. So Socorro itself, it's not yet been completely proven, but there are people that have proposed that the activity at Socorro is a remnant of a small hotspot. But the one in Hawaii is hotspot activity. The one in the Azores is hotspot activity. The one in the Canaries is hotspot activity. So more than often not, these are associated more with alkaline magmas, with trace elements and volatile contents that suggest that we're looking at tapping mantle that is probably not like mid-ocean ridge. So Klaus and I were talking today, we said, so would this kind of eruption occur in a tholite, in a normal mid-ocean ridge, maybe shallow, say in Iceland on the Reykjanes Ridge, where the mid-ocean ridge becomes very shallow, would you get this kind of activity there? We don't know. It may not have enough gas content. We think there is a geodynamic association perhaps with this particular style. So not only a water depth, but a larger geodynamic relationship.
Pregunta?
Oh, and before I answer the question, one year ago when we were out on the Nautilus, Klaus celebrated his birthday, and as is the tradition on the Nautilus, when it's your birthday on the Nautilus, they bake you a beautiful cake. And so here's Klaus enjoying his birthday cake. Sorry, yes, question.
Hi.
Yeah.
Thank you very much for your talk.
Yeah.
The quantity and size of the buoyant scoria can tell something about the volume of the eruption, or is just more a casualty?
Yeah, that's a very good question. We think that in actuality, the proportion of buoyant scoria that actually make it to the sea surface is a very, very small fraction of the volume of the material that's produced at the vent. So it's really difficult to infer much about the volume, the erupted volume from what pops up on the surface. But, yeah.
Maybe two questions. The eruption that you show in West Mata,
Yeah,
did it produce vesiculated scoria?
it did.
Okay. And this was
Sorry, and I should point out that was about 1,000 meters water depth.
Yeah. So maybe it's just a matter of each gas content in the magma has a depth of range when the water pressure and gas pressure can balance and produce the
Yeah, West Mata is in a subduction zone environment, and I think it was a basaltic andesite, but the rocks in subduction zone environments typically have higher water and CO2 content. So, yes, I think you're right. I think, well, the question is, it produced scoria at Mata, but it didn't produce scoria that was buoyant. So, because I think the water depth is so great, so the volume fraction of bubbles in the scoria, when it's produced at 1,000 meters, is not large enough so it can rise up. You need to be at a certain depth where the volume of the gas in the scoria is big enough so the scoria itself is less dense than seawater. So you're not going to generate the buoyant scoria in deep water, even if you have high gas volume contents, I think. And then the second question?
No.
Yes. On the left.
What's the relationship to the Socorro Island rocks? Because all these places are close to islands that are of volcanic origin. So it's a continuation of the process that formed those islands, or some sort of.
Yeah, so Socorro is a fairly mature island, and it's the only peralkaline. It's the only volcano that produces peralkaline magmas in the Pacific Ocean basin. And when we did the multi-beam mapping of Socorro Island, it's clear that, well, on Socorro Island itself, the sides of the main part of the volcano is littered by scoria cones, so subsidiary vents to the main volcano. And that just continues offshore. So when you go offshore, you look at the multi-beam map, and you see all of these small eruptive centers that are probably transient, they don't last for very long. But overall, they have built up the island to a certain level. The Socorro eruption, which occurred offshore, may be magma that's bypassing, so there's probably a magma chamber under Socorro, because they're very evolved silicic rocks that have been erupted at Socorro that probably require a large magma chamber to evolve them to silicic compositions. The basalts that are erupted underwater and that are on the sides of Socorro may be magmas that are bypassing the main magma chamber and erupting on the periphery.
Thank you. And for a very nice talk.
Oh, thank you.
¿Alguna otra pregunta? Bueno, si va a ser la pregunta que se hizo en el Facebook. Yo creo que es de Silvia Elizabeth González y pregunta: ¿se sabe cuántos volcanes marinos existen? Se tradujo: do we know how many marine volcanoes exist? This is a Facebook question. Do you have the exact number, please?
Oh, the exact number, that's 867,342. There are thousands and thousands of underwater volcanoes. If you look at a submarine map of the Pacific Ocean, it's filled with seamounts, each of which are small submarine volcanoes that have formed off-axis from major spreading sites. So there are almost more than you can count.
I think that's worth remembering. There's a lot of work for the cruises to go. So, well, if you see a floating rock, then you know who to ask for. Si ven una roca flotante cerca de la playa, ahí saben con quién llamar. Bueno, muchas gracias por su atención. Pues nada más hacer un poco de propaganda. Hay unas charlas de la próxima semana que van Va a darlas Guillermo Alvarado de Costa Rica. Las charlas van a ser el martes 13 y jueves 15 a las 12 horas. Y los títulos son los flujos piroclásticos del volcán Arenal entre 1968 y 2010 y la actividad eruptiva del Puri-Alba entre 2010 y 2018 y también va a hablar posiblemente de lahares. Entonces, bueno, los esperamos aquí, tan numerosos como hoy. Muchas gracias.